So here's something worth thinking about as you settle in tonight. Right now, at this very moment, about 93 million miles away from you, there is a ball of gas so massive that it contains 99.8% of all the mass in our entire solar system. And deep in the core of that ball, where the pressure is so intense it would crush anything we've ever built, where the temperature reaches about 15 million degrees, hydrogen atoms are being squeezed together so hard that they stop being hydrogen and become something else entirely. They become helium. And in that transformation, in that moment where 4 hydrogen nuclei fuse into one helium nucleus, a tiny bit of mass simply vanishes. It doesn't go somewhere. It doesn't hide. It converts into energy, pure energy, according to the most famous equation ever written. And that energy is what warms your face on a summer afternoon. That energy is what grew the food you had for dinner. That energy, born from fusion in the belly of a star, is what makes life on this planet possible at all. And for about a century now, some of the smartest people who have ever lived have been trying to figure out how to do that same thing here on Earth. How to take the power source of the stars and put it in a building. How to bottle a sun. And that story, the story of nuclear fusion, how it works, why it's so extraordinarily difficult, and how we're closer than we've ever been to actually pulling it off. That's what we're going to talk about tonight. Slowly, gently, one piece at a time. If you fall asleep somewhere in the middle, that's perfectly fine. That's kind of the point. But if you stay with me, I think you'll find this is one of the most fascinating engineering challenges humans have ever attempted. Let's start at the very beginning, though. Not with the engineering, not with the reactors and the magnets and the plasma. Let's start with the question that came first, the question that puzzled scientists for centuries before anyone even knew what an atom was. Where does the sun get its energy? Think about how strange that question really is. People have been looking up at the sun for as long as there have been people, and for most of human history, nobody had any idea what it actually was. The ancient Greeks thought it might be a chariot of fire. Various cultures imagined it as a god, a spirit, a lantern hung in the sky. But even as science began to mature in the 1700s and 1800s, the sun's energy source remained genuinely mysterious. And it wasn't a trivial mystery. It was a deep, uncomfortable one, because the numbers didn't work. Here's what I mean. By the mid-1800s, scientists had a pretty good handle on chemistry. They understood combustion. They knew how much energy you could get by burning things. So naturally, someone asked the obvious question. What if the sun is just burning? What if it's a giant ball of coal or some kind of fuel, and it's on fire? Well, you can actually calculate how long a sun-sized ball of coal would last if it were burning. And the answer is about 5,000 years. That's it. 5,000 years, and you'd burn through the whole thing. But geologists were already finding evidence that the Earth was far, far older than 5,000 years. Hundreds of millions of years old at least. So whatever was powering the sun, it wasn't chemical combustion. It couldn't be. The energy budget just didn't balance. In the 1850s, 2 brilliant physicists, Lord Kelvin in Britain and Hermann von Helmholtz in Germany, independently proposed a different idea. What if the sun was slowly contracting under its own gravity? As it shrinks, gravitational potential energy converts to heat. This is a real effect. It's called the Kelvin-Helmholtz mechanism, and it actually does produce energy. But when you run the numbers on this one, you get maybe 20 to 30 million years of sunshine, which sounds like a lot, but it still wasn't enough. Darwin's theory of evolution, published in 1859, demanded hundreds of millions of years for life to have evolved. Geologists were finding rocks that appeared to be billions of years old. And here was Lord Kelvin, one of the most respected physicists in the world, insisting that the sun couldn't possibly be more than about 20 or 30 million years old, because there was simply no known energy source powerful enough to sustain it longer than that. Kelvin was wrong, of course. But here's the thing. He was wrong for a completely reasonable reason. He was wrong because the energy source that actually powers the sun involves physics that hadn't been discovered yet. He couldn't have known. Nobody could have. The answer required an entirely new understanding of matter itself. And that understanding started to arrive right around the turn of the 20th century. In a rush of discoveries that came so fast, they must have felt almost overwhelming. In 1895, Wilhelm Röntgen discovered X-rays. In 1896, Henri Becquerel discovered radioactivity almost by accident. He left some uranium salts sitting on a photographic plate in a drawer, and when he developed the plate, he found it had been exposed. The uranium was emitting something, some kind of radiation, all on its own, without any external energy input. Marie and Pierre Curie followed up on Becquerel's work and discovered radium and polonium, elements that were intensely radioactive, that seemed to pour out energy from somewhere inside themselves. This was deeply strange. Where was this energy coming from? These radioactive materials weren't burning. They weren't being compressed. They were just sitting there, radiating energy, sometimes for years. It violated everything classical physics said about energy conservation, unless the energy was coming from somewhere inside the atom itself. And that idea, that atoms contained vast stores of internal energy, was revolutionary. It hinted that matter was far more energetic than anyone had imagined. Then in 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that changed everything. Albert Einstein's special theory of relativity included a short, almost casual derivation, showing that mass and energy are equivalent. E equals mc squared. Energy equals mass times the speed of light squared. And the speed of light is an enormous number, about 300 million meters per second. Square that, and you get a number so large it's hard to comprehend. What this equation tells you is that a tiny, tiny amount of mass contains a staggering amount of energy. A single gram of matter, if you could convert it entirely to energy, would release about 90 terajoules. That's roughly the energy of the Hiroshima bomb. From 1 gram. Now, Einstein didn't immediately connect this to the sun. That took a while, but the pieces were falling into place. In 1911, Ernest Rutherford's famous gold foil experiment revealed that atoms have a tiny, dense nucleus at their center, surrounded by orbiting electrons. The nucleus was where almost all the mass was concentrated, packed into an incredibly small space. And by the 19-teens and 20s, physicists were beginning to understand that the nucleus was made up of protons and, eventually, neutrons, held together by an extraordinarily powerful force, what we now call the strong nuclear force. Here's where it starts to connect to fusion. Francis Aston, a British physicist working at Cambridge, built an instrument called a mass spectrograph that could measure the masses of different atoms with extraordinary precision. And in 1920, he made a remarkable discovery. He found that the mass of a helium atom was slightly less than the combined mass of 4 hydrogen atoms. Not by much. The difference was less than 1%. But it was real, and it was measurable. And if you applied Einstein's equation to that missing mass, the energy it represented was enormous. Arthur Eddington, the great British astrophysicist, seized on this almost immediately. In a lecture to the British Association for the Advancement of Science in 1920, Eddington proposed that the sun's energy came from the conversion of hydrogen into helium deep in its interior. He argued that if about 4 hydrogen nuclei could somehow fuse together to form one helium nucleus, the missing mass, that tiny fraction of a percent, would be converted to energy according to E equals mc squared. And because the sun contains such an incomprehensibly vast amount of hydrogen, this process could power it for billions of years, not millions, billions. Think about what a leap that was. In one stroke, Eddington resolved the great puzzle that had stumped Kelvin and Helmholtz. The sun wasn't burning. It wasn't contracting. It was fusing. It was converting mass directly into energy through nuclear reactions, and it had enough fuel to keep doing so for roughly 10 billion years. Our sun is about 4.5 billion years old right now, so it's roughly middle-aged. It's got another 5 billion years or so of hydrogen fusion left in it, which is a comforting thought, honestly. But Eddington's proposal immediately raised a fierce objection, and it came from a very specific and very real problem in physics. If the sun's core is about 15 million degrees, which was the best estimate at the time, and it turns out to be pretty accurate, then the hydrogen nuclei in that core are moving fast. Very fast. But here's the thing. Hydrogen nuclei are protons. They carry a positive electrical charge, and positive charges repel each other. This is Coulomb's law, basic electrostatics. 2 protons approaching each other experience an increasingly powerful repulsive force as they get closer. And when you calculate how much energy a proton at 15 million degrees actually has, it's not enough. Not even close. The protons in the sun's core, even at those incredible temperatures, don't have enough kinetic energy to overcome the electrical repulsion between them and get close enough to fuse. Classically, it's impossible. The sun shouldn't work. And this is where quantum mechanics enters the story. And honestly, this is one of my favorite parts because it's so wonderfully strange. In 1928, a young physicist named George Gamow, a Ukrainian-born theorist who was brilliant and also famously playful, the kind of guy who'd put jokes in his scientific papers, Gamow applied the new quantum mechanics to the problem of nuclear barriers. He showed that in quantum mechanics, particles don't have a definite position. They're described by a wave function, a probability distribution. And one of the strangest consequences of this is that a particle can sometimes appear on the other side of a barrier that it classically doesn't have enough energy to cross. It's called quantum tunneling, and it's not a metaphor. It's a real, measurable phenomenon. Particles genuinely do this. They tunnel through energy barriers that should be impenetrable. Gamow calculated the probability of a proton tunneling through the Coulomb barrier, that wall of electrical repulsion, and reaching another proton closely enough for the strong nuclear force to grab hold and pull them together, and the probability for any single pair of protons is absurdly small, fantastically tiny. But here's the thing about the Sun. Its core contains an almost inconceivable number of protons, something like 10 to the 57th power. And they're all bouncing around, colliding with each other billions of times per second. So even though the probability of any single fusion event is vanishingly small, when you multiply that tiny probability by the enormous number of attempts happening every second, you get a steady, reliable rate of fusion. Enough to power a star. It's a bit like a lottery. Any individual ticket has almost no chance of winning. But if you buy trillions upon trillions of tickets every second for billions of years, you're going to win constantly. The Sun is essentially winning the quantum lottery every moment of every day, and it has been for 4.5 billion years. So by the late 1920s, the theoretical picture was coming together. Scientists understood that fusion was possible, that quantum tunneling made it work even at temperatures that classical physics said weren't high enough, and that the conversion of mass to energy via Einstein's equation could explain the Sun's seemingly inexhaustible power output. But there was still a missing piece. They knew hydrogen was turning into helium, but they didn't know the exact sequence of steps. What was the actual chain of reactions? How did 4 separate protons end up as a single helium nucleus? Because it doesn't happen all at once. 4 protons don't just slam together simultaneously. That would be fantastically unlikely, even by quantum standards. There had to be intermediate steps, a chain of reactions, each one leading to the next. And figuring out that chain, the specific nuclear reactions that power the Sun, that puzzle fell to a young German-American physicist who had recently fled Nazi Germany and was working at Cornell University in upstate New York. His name was Hans Bethe, and what he figured out in 1938 and 1939 would earn him the Nobel Prize and give us our first complete understanding of how stars actually burn their fuel. Bethe's insight was elegant, and it came in 2 flavors, 2 different reaction chains that both accomplish the same basic thing, which is turning hydrogen into helium and releasing energy along the way. But they do it through different intermediate steps, and which one dominates depends on the size and temperature of the star. The first one is called the proton-proton chain, and it's the one that powers our Sun. Let's walk through it slowly, because it's actually beautiful in its simplicity once you see how it works. Picture 2 protons, 2 hydrogen nuclei, drifting toward each other inside the Sun's core. They get close enough, thanks to the incredible pressure and temperature down there, and quantum tunneling lets them overcome their mutual electrical repulsion. They fuse. But here's the thing. 2 protons stuck together would be helium-2, and that's incredibly unstable. It flies apart almost instantly. So for this reaction to actually work, something else has to happen at the exact same moment. One of those protons has to undergo what's called a beta plus decay, transforming into a neutron. When it does that, it spits out a positron and a tiny ghostly particle called a neutrino. So what you end up with after this first step isn't 2 protons stuck together. It's 1 proton and 1 neutron bound together. That's deuterium, heavy hydrogen. And this first step, This proton-proton fusion into deuterium is actually the slowest step in the entire chain. It's the bottleneck. On average, a given proton in the sun's core will bounce around for about 1 billion years before it successfully completes this reaction. 1 billion years. That's how unlikely it is. And yet, there are so many protons in the sun's core, something like 10 to the 57th power of them, that even with each individual proton waiting 1 billion years for its turn, the reaction is happening constantly, steadily, reliably, billions upon billions of times every second. Once you've got deuterium, though, things speed up dramatically. That deuterium nucleus quickly captures another proton, and this time, the reaction is much easier. It happens in a matter of seconds. What you get is helium-3, a light isotope of helium with 2 protons and 1 neutron. And then, for the final step, 2 of these helium-3 nuclei find each other and fuse together. When they do, they form a regular helium-4 nucleus, 2 protons, 2 neutrons, and they kick out 2 spare protons in the process. Those 2 protons go back into the pool, free to start the whole cycle again. So the net result, when you add it all up, is that 4 protons have become 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and a bunch of energy. The positrons immediately annihilate with electrons, producing gamma-ray photons. The neutrinos zip right out of the sun. They barely interact with matter at all, just ghosting through the entire solar body in about 2 seconds. And the gamma rays? They begin an incredibly long, slow journey outward, bouncing and scattering off particle after particle, being absorbed and re-emitted millions of times, gradually losing energy and shifting from gamma rays down to X-rays, then ultraviolet, and eventually visible light. That journey from the core to the surface takes somewhere on the order of 100,000 to 200,000 years. So the sunlight hitting your face on a warm afternoon actually began as a gamma ray from a fusion reaction deep in the sun's core, back when woolly mammoths were still roaming the earth, or even earlier. Think about that for a second. The light is ancient by the time it reaches the surface, and then it makes the 93 million mile trip from the sun to your skin in just 8 minutes. Now, that's the proton-proton chain, and it's the dominant energy source in stars like our sun, stars that are roughly the sun's mass or smaller. But Beth also worked out a second pathway, and this one is even more clever. It's called the CNO cycle, which stands for carbon, nitrogen, oxygen. In larger, hotter stars, stars may be 50% more massive than the sun or bigger. The core temperatures are high enough to drive a different set of reactions, and these reactions use carbon as a catalyst. The carbon isn't consumed. It participates in the reactions, gets transformed into nitrogen, then oxygen, then back to carbon again, and along the way, 4 protons get converted into 1 helium nucleus, just like in the proton-proton chain. Same inputs, same outputs, but a completely different pathway. It's like 2 different routes to the same destination. And here's what's really clever. The carbon-12 nucleus you start with is the same carbon-12 nucleus you end with. It's recycled. It just facilitates the process, like an enzyme in biology. Beth published his analysis of the CNO cycle in 1939, and it was a masterwork of theoretical physics. He reportedly worked out much of it during a train ride. which is one of those details that sounds apocryphal but appears to be more or less true. He won the Nobel Prize in Physics in 1967 for this work, almost 3 decades later. So by 1939, humanity had a remarkably complete picture of how stars work. We understood that fusion was the energy source. We knew the specific reaction chains. We could calculate the energy output, and it all matched the observations. The sun's luminosity, its temperature, its age, everything fit. It was one of the great triumphs of 20th century physics. This convergence of quantum mechanics, nuclear physics, and astrophysics all coming together to explain why stars shine. But here's where the story takes a darker turn, because the very next question, the one that was already forming in the minds of physicists on both sides of the Atlantic, was obvious and inevitable. If you can release that much energy by fusing light nuclei together, can you do it here on Earth? Can you build a fusion device? And the answer, as the world would learn in the most terrible way, imaginable, was yes. The first human-made fusion reactions on Earth didn't happen in a power plant. They happened in a bomb. And the path to that bomb ran through fission first. You probably know the broad strokes. The Manhattan Project. The race to build an atomic weapon before Nazi Germany could. The Trinity test in July 1945. And then Hiroshima and Nagasaki. Those were fission bombs. They worked by splitting heavy atoms, uranium-235 and plutonium-239, not by fusing light ones. But even during the Manhattan Project, even before the first fission bomb had been tested, one physicist was already pushing hard for something far more powerful. His name was Edward Teller, a Hungarian-born physicist with enormous intellect and enormous ambition, and he was obsessed with the idea of a fusion bomb, what would come to be called the hydrogen bomb, or the super. Teller's idea was conceptually straightforward, even if the engineering was nightmarishly complex. You use a fission bomb as a trigger, as a match, essentially, to create the extreme temperatures and pressures needed to ignite fusion in a mass of hydrogen isotopes. A fission bomb produces temperatures of tens of millions of degrees, which is right in the range where fusion becomes possible. So you're using one kind of nuclear weapon to light the fuse on a much more powerful kind. And unlike fission bombs, which have a practical upper limit on their yield because of the critical mass constraints, a fusion bomb has no theoretical upper limit. You can just keep adding more fusion fuel. That's a terrifying thought, and it was terrifying to many of the physicists who understood it. There was a fierce debate within the scientific community and the government about whether to pursue the hydrogen bomb. Robert Oppenheimer, who had led the Manhattan Project, opposed it on moral and strategic grounds. He argued that it was a weapon of genocide, not a weapon of war, that there was no military target large enough to justify the kind of destruction a hydrogen bomb could cause. Teller pushed relentlessly for it. The debate tore the physics community apart and ultimately destroyed Oppenheimer's career. His security clearance was revoked in 1954, in a hearing that many historians view as a politically motivated travesty, driven in part by Teller's testimony against him. It's one of the saddest chapters in the history of American science, and the wounds it left took decades to heal. But the bomb got built. The key breakthrough came from the mathematician Stanislaw Ulam, who in early 1951 came up with a new configuration, a way to use the radiation from a fission primary to compress and heat a separate fusion secondary. Teller refined the idea, and the design became known as the Teller-Ulam configuration. It's still the basic architecture of every thermonuclear weapon in the world today. The first full-scale test, codenamed Ivy Mike, took place on November 1st, 1952, on the island of Alugalab in the Marshall Islands. The device used liquid deuterium as its fusion fuel and weighed about 82 tons. It was more of a building than a bomb, completely impractical as a weapon. But it worked. The yield was 10.4 megatons, roughly 700 times more powerful than the bomb that destroyed Hiroshima. The fireball was over 3 miles wide. The island of Alugalab simply ceased to exist. In its place was an underwater crater a mile across and 200 feet deep. The Soviet Union tested their own thermonuclear device less than a year later, in August 1953. The arms race was on, and it would define the next 4 decades of human civilization, the constant, low-grade terror of mutually assured destruction. Thousands of warheads pointed at cities on both sides, the fate of the species hanging on the decisions of a handful of political leaders and the reliability of early warning systems that sometimes malfunctioned. There were close calls, closer than most people realize. But here's the thing about the hydrogen bomb. From a purely technical standpoint, it proved that fusion could be achieved on Earth. Not in a useful way, not in a controlled way, but it demonstrated that human beings could create the conditions necessary to fuse hydrogen isotopes and release enormous amounts of energy. The temperatures, the pressures, the confinement, it was all brute force, all uncontrolled, all destructive. But the physics worked, and that raised an obvious, tantalizing, almost impossibly hopeful question. Could you do the same thing, but slowly? Could you tame it? Could you build a device that sustained fusion reactions, not in a single explosive microsecond, but continuously, steadily, the way the sun does it, and use that energy to generate electricity? Because if you could do that, you would solve the energy problem, not just for a generation, not just for a century, but essentially forever. The fuel for fusion, hydrogen isotopes, primarily deuterium and tritium, is virtually inexhaustible. Deuterium can be extracted from ordinary seawater. Every gallon of seawater contains about 1/6 of a gram of deuterium, which doesn't sound like much until you realize that the fusion energy in that tiny amount is equivalent to about 300 gallons of gasoline. The oceans contain enough deuterium to power human civilization at current energy consumption levels for billions of years. Billions. And unlike fission, fusion produces no long-lived radioactive waste, no risk of meltdown, no chain reaction that can run away. The reaction is inherently self-limiting. If something goes wrong, the plasma cools and the fusion simply stops. It's the opposite of a fission reactor in that regard. So the prize was almost unimaginably large, clean, safe, virtually limitless energy. And in the early 1950s, as the Cold War deepened and both superpowers poured resources into nuclear research, programs to develop controlled fusion began in earnest. In secret, on both sides of the Iron Curtain. The Americans, the Soviets, and the British all launched classified fusion research programs within a few years of each other. each working independently, each convinced they were on the verge of a breakthrough. And each one, in those early years, ran headlong into the same brutal reality that controlling fusion, taming that star fire, and keeping it burning steadily in a machine was going to be one of the hardest engineering challenges humanity had ever faced. And to understand why, you need to think about what you're actually asking a machine to do. You're asking it to hold a gas, except it's not really a gas anymore. It's a plasma, which is this roiling, turbulent soup of stripped-down atoms and free electrons. And you're asking it to hold that plasma at temperatures of around 100 million degrees. Not 100 million degrees Fahrenheit or Celsius, by the way. At those temperatures, the scales barely matter. They converge. But 100 million degrees Kelvin, that's roughly 6 to 10 times hotter than the core of the sun. And you might wonder, wait, why do we need to go hotter than the sun? The sun manages to fuse hydrogen at only about 15 million degrees. Why can't we just do what the sun does? And the answer is gravity. The sun has an enormous advantage that no machine on Earth can replicate. It has the gravitational weight of 330,000 Earths pressing inward on its core. That incredible pressure means the hydrogen nuclei in the sun's core are squeezed together at extraordinary densities. So even though any individual proton has a relatively low probability of tunneling through the Coulomb barrier and fusing at 15 million degrees, remember, that first step in the proton-proton chain takes 1 billion years on average for any given proton. There are so fantastically many protons crammed together that the total rate of fusion is enormous. The sun can afford to be inefficient on the individual level because it makes up for it in sheer volume and density. We can't do that. We can't create that kind of gravitational pressure in a laboratory. So instead, we compensate by cranking up the temperature. Higher temperature means the particles are moving faster, slamming into each other harder, and the probability of quantum tunneling through the Coulomb barrier goes up dramatically. You're basically trading pressure for temperature. And it turns out that to get a useful rate of fusion in a reasonably sized machine at achievable densities, you need temperatures in the neighborhood of 100 to 200 million degrees. Which brings us to the fundamental problem. What do you build the container out of? Think about that for a second. No material on Earth can withstand 100 million degrees. The hottest melting substance we know of, something like tungsten or tantalum hafnium carbide, melts at around 4,000 degrees. 100 million degrees is 25,000 times hotter than that. If your plasma touches the wall of your container, two things happen, both of them bad. First, the wall material vaporizes and contaminates your plasma with heavy atoms, which radiate energy away and cool the plasma down, killing the fusion reaction. Second, you lose enormous amounts of energy to the wall because the plasma is dumping its heat into the structure instead of sustaining fusion. So the plasma absolutely cannot touch the walls. You need to confine it, suspend it in space, keep it away from any material surface, while simultaneously heating it to temperatures that exist nowhere else in the solar system except inside stars. This is the confinement problem, and it's the central engineering challenge of fusion energy. It's what makes fusion so maddeningly difficult, and it's what all the major experimental approaches have been trying to solve for the past 70 years. Now, in those early classified programs of the 1950s, researchers on all sides came up with essentially the same insight, independently. If you can't use a physical container, what about a magnetic one? Plasma is made of charged particles, positive ions and negative electrons, and charged particles respond to magnetic fields. A moving charged particle in a magnetic field follows a curved path, spiraling around the magnetic field lines. So if you could arrange magnetic fields in just the right geometry, you could, in principle, create an invisible magnetic bottle that would hold the plasma in place, keeping it away from the walls, suspended in the middle of a vacuum chamber while you heated it to extraordinary temperatures. Here's the thing. The concept is simple. The execution is nightmarishly difficult, and the early attempts proved that almost immediately. In the United States, one of the first major approaches was a device called a stellarator, conceived by Lyman Spitzer, an astrophysicist at Princeton. Spitzer was a fascinating character, primarily known for his work on interstellar matter and the physics of stars. He was also an avid mountaineer and skier, and he had this restless intellectual energy that made him willing to tackle problems way outside his usual lane. The story goes that in 1951, Spitzer read a news report about an Argentine physicist named Ronald Richter, who claimed to have achieved controlled fusion. Richter's claims turned out to be completely bogus. The Argentine government under Perón had poured money into his project, and it was essentially a fraud. But the news report got Spitzer thinking. On a ski trip, of all places, he started sketching out ideas for a magnetic confinement device, and he came up with the stellarator concept. The basic idea was to create a magnetic field inside a tube bent into a figure-8 shape, or more precisely, a toroidal shape with a twist. See, if you just bend a tube into a simple donut, a torus, and run a magnetic field around it, you get a problem. The magnetic field is stronger on the inside of the donut than on the outside because the field lines are more compressed on the inner curve. That gradient causes the plasma particles to drift. Ions drift one way, electrons drift the other, and the plasma quickly escapes. It's unstable. Spitzer's insight was that by twisting the tube, by giving it that figure-8 shape, you could cancel out those drifts. Particles that were on the outside of the curve on one part of their journey would be on the inside on another part, and the drifts would average out. Spitzer took his idea to the Atomic Energy Commission, and the classified program that resulted was called Project Matterhorn, based at Princeton. They built a series of stellarators through the 1950s, the Model A, the Model B, the Model C, each one larger and more sophisticated, and each one ran into problems. The plasma was wildly unstable. It would develop turbulence, kinks, sausage-like pinches, all sorts of instabilities that caused it to escape the magnetic confinement far faster than theory predicted. The energy confinement times were terrible. Instead of holding the plasma long enough for fusion to occur, the magnetic bottle was leaking like a sieve. Meanwhile, in Britain, a team at Harwell and later at the Atomic Energy Research Establishment was working on a different approach called the pinch. The idea here was even simpler in concept. You run a huge pulse of electrical current directly through the plasma itself. That current generates its own magnetic field, which wraps around the plasma column and squeezes it inward, pinches it. If you could pinch it hard enough and fast enough, maybe you could compress and heat the plasma to fusion conditions, at least briefly. The British program had a machine called ZETA, the Zero Energy Thermonuclear Assembly, which was built at Harwell and began operating in 1957. And in January of 1958, the British made a dramatic announcement. They held a press conference, and the newspapers went wild. The headlines said that Britain had achieved thermonuclear fusion. Zeta was producing neutrons, which is one of the signatures of fusion reactions. It was a sensation. The scientists involved were cautious in their published papers, but the media coverage was triumphant. And then, within months, it fell apart. Further analysis showed that the neutrons Zeta was producing weren't coming from thermonuclear fusion. They were coming from a completely different process. The plasma instabilities in the pinch were accelerating individual ions to high energies, and those fast ions were slamming into other particles and producing neutrons through what you might call beam target reactions, not the thermal fusion you'd need for a power plant. The plasma wasn't uniformly hot enough for real fusion. The instabilities were actually the source of the neutrons, not a sign that fusion was working. It was deeply embarrassing. The scientists involved, people like John Cockcroft, who was a Nobel laureate and the director of Harwell, had to walk back the claims publicly. It was a painful lesson about how easy it is to fool yourself in plasma physics and how tricky it is to distinguish real thermonuclear fusion from other processes that can mimic its signatures. The Soviets, meanwhile, were working on their own approaches, also in secret. And here's where one of the most important ideas in the entire history of fusion research emerged. In the early 1950s, two Soviet physicists, Andrei Sakharov and Igor Tamm, proposed a device that would become the most successful and widely adopted approach to magnetic confinement. Sakharov, who would later become world famous as a dissident and human rights advocate, was at this point a young theoretical physicist deeply embedded in the Soviet nuclear weapons program. He and Tamm proposed a toroidal chamber with magnetic coils, a tokamak from the Russian words for toroidal chamber with magnetic coils, toroidalnaya, camera S, magnetnimi, katushkami. The tokamak used a different strategy from the stellarator. Instead of relying on the external shape of the chamber to create the necessary twist in the magnetic field, the tokamak drove a large electrical current through the plasma itself. That plasma current generated its own magnetic field, which combined with the external toroidal field to create the helical, twisted field lines you need to confine the plasma. It was, in a sense, a more elegant solution. The plasma was doing part of the confinement work itself. But in the 1950s and early 60s, the Soviet tokamak results weren't dramatically better than anyone else's. Everyone was struggling with the same fundamental problems: plasma instabilities, energy losses, confinement times that were orders of magnitude too short. And then came 1958, and something remarkable happened that changed the entire landscape of fusion research. It wasn't a scientific breakthrough. It was a political decision. At the Second United Nations International Conference on the Peaceful Uses of Atomic Energy, held in Geneva, the major powers agreed to declassify their fusion research programs. The Americans, the Soviets, The British, they all opened their books, and what they discovered was both humbling and oddly comforting. Everyone was stuck. Everyone was dealing with the same plasma instabilities, the same disappointing confinement times, the same gap between theoretical predictions and experimental reality. No one was secretly ahead. The grand optimism of the early 50s, the belief that controlled fusion was maybe 5 or 10 years away, had crashed into the hard physics of plasma behavior. And so the researchers did something that would have been unthinkable in most areas of Cold War science. They started talking to each other, sharing data, collaborating across ideological lines. Fusion became one of the first truly international scientific endeavors of the nuclear age. But even with collaboration, progress was agonizingly slow through the early 1960s. The plasma, it turned out, had a seemingly infinite repertoire of ways to misbehave. Every time you solved one instability, another one appeared. The theorists would predict a certain confinement time based on classical physics, how often particles collide and scatter, and the experiments would come in 10 or 100 times worse. The plasma was losing energy through some mechanism that nobody fully understood, a kind of anomalous transport that seemed to mock every theoretical model. Some researchers started to quietly wonder whether magnetic confinement would ever work at all. And then, in the mid-1960s, something started to change in Moscow. A team led by Lev Artsimovich, a brilliant and forceful Soviet physicist who ran the tokamak program with an iron hand, began getting results from a machine called the T3 tokamak that were genuinely startling. The electron temperatures they were measuring, and this is the key number, the one that everyone cared about, were coming in at around 10 million degrees Celsius. Now, that might not sound like a lot compared to the 100 million degrees you ultimately need for fusion, but here's the thing. It was an order of magnitude better than what anyone else in the world was achieving at the time. And even more importantly, the confinement times, how long the plasma stayed hot and dense before it leaked away, were far, far better than what the stellarators and pinch devices were managing. The T3 was holding on to its plasma maybe 30 times longer than what Bohm diffusion predicted. And that was the real headline, because Bohm diffusion was this pessimistic scaling law that had haunted magnetic confinement for over a decade. It basically said that plasma would always leak out of a magnetic bottle much faster than classical theory predicted, and the bigger you made the machine, the worse it got, relative to what you needed. If Bohm diffusion was the final word, then magnetic fusion was probably a dead end. But the T3 results were saying something different. They were saying the tokamak configuration somehow tamed whatever was causing that anomalous transport. The plasma was behaving closer to what classical theory predicted. It was still not perfect, still losing energy faster than ideal, but it was so much better that it changed the entire calculation about whether fusion was feasible. The problem was, nobody outside Moscow believed it. And you can understand why. Remember what had happened with Zeta in Britain just a few years earlier. That premature announcement of fusion that turned out to be completely wrong. Neutrons from beam target reactions rather than thermonuclear conditions. That embarrassment had made the entire fusion community deeply skeptical of dramatic claims. And here were the Soviets, in the middle of the Cold War, announcing results that were almost too good to be true. The Western researchers were polite about it, but privately, many of them thought the Soviet diagnostics must be wrong. Maybe they were measuring the ion temperature instead of the electron temperature. Maybe their instruments were miscalibrated. Maybe there was some systematic error they weren't accounting for. The numbers were just too good. So Artsimovich did something clever. He invited a team from the Culham Laboratory in England, the same lab that had inherited the Zeta program, to come to Moscow and independently verify the T3 results using their own diagnostic equipment. Specifically, the British team brought a technique called Thomson scattering, which uses laser light to measure electron temperature directly and unambiguously. You fire a laser beam into the plasma. The photons scatter off the electrons, and the spectrum of the scattered light tells you exactly how fast those electrons are moving, which tells you their temperature. It's a clean measurement, very hard to argue with. The British team arrived in Moscow in 1969, set up their equipment on the T3, and ran the experiments. And the results confirmed everything Artsimovich had claimed. The electron temperatures were real. The confinement was real. The tokamak was genuinely, measurably, dramatically outperforming every other magnetic confinement concept in the world. The effect on the fusion community was like a thunderclap. Almost overnight, the tokamak went from being one of several competing approaches to being the frontrunner. Labs around the world started converting their machines to the tokamak configuration or building new tokamaks from scratch. Princeton, which had been the home of the Stellarator for over 15 years, Spitzer's baby, the machine he'd poured his career into, Princeton pivoted. They converted their largest Stellarator, the Model C, into a tokamak. They literally took apart the Stellarator and rebuilt it as a symmetric torus with a plasma current, and when they turned it on, they immediately got better results than the Stellarator had ever achieved. That must have been bittersweet for Spitzer, who was still at Princeton. His concept wasn't wrong exactly. Stellarators would eventually come back decades later with much more sophisticated designs, but in the late 1960s, the tokamak was simply better at the one thing that mattered most, keeping plasma hot and confined. So what was it about the tokamak that worked so well? Let's think about this for a second, because it's actually a beautiful piece of physics. In a tokamak, you have a donut-shaped vacuum chamber, and you create a strong magnetic field that wraps around the donut the long way. This is called the toroidal field, generated by external magnets. But you also drive a large electrical current through the plasma itself, flowing around the donut the long way. That current creates its own magnetic field, which wraps around the plasma the short way, the poloidal field. When you combine these two fields, the toroidal and the poloidal, the resulting magnetic field lines trace out helical paths, spiraling around the donut like the stripes on a barber pole. And it's this helical structure that provides good confinement, because the charged particles, as they follow these spiraling field lines, spend time on both the inside and outside of the donut and the drifts that would otherwise push them outward. Those drifts that plagued simple toroidal devices get averaged out. The particles drift outward on one part of their orbit and inward on another, and over many trips around the torus, the net drift is much smaller. Now, Here's a subtle but important detail. That plasma current that creates the colloidal field? In a tokamak, you drive it using the plasma itself as the secondary winding of a giant transformer. There's a big iron core or air core in the center of the machine, and you ramp a current through the primary winding, which induces a voltage around the torus, which drives current through the plasma. It's the same principle as any electrical transformer you'd find in a power supply, except one of the windings is a ring of superheated ionized gas. And this is clever, but it also creates a fundamental limitation. A transformer only works when the current in the primary is changing. Once it reaches its maximum value, the induced voltage drops to zero, and the plasma current starts to decay, which means a basic tokamak is inherently a pulsed device. It can only run for a limited time before you have to reset the transformer and start over. This would become one of the central engineering challenges for anyone trying to turn a tokamak into a power plant, because power plants need to run continuously, not in pulses. But that was a problem for later. In the early 1970s, the immediate challenge was scaling up, and scale up they did. The 1970s were the golden age of tokamak construction. The United States built a series of increasingly ambitious machines. Princeton built the Princeton Large Torus, or PLT, which achieved ion temperatures of over 60 million degrees in 1978, genuinely in the range where deuterium-tritium fusion becomes significant. Oak Ridge built ORMAC. MIT built Alcator, a compact, high-field design that pioneered the use of very strong magnetic fields to improve confinement. The Europeans formed a multinational collaboration and built JET, the Joint European Torus, in Culham, England, the same site where Zeta had stood. The Japanese built JT-60. The Soviets continued building larger tokamaks. It was an international race, and the progress was real and measurable. The key metric that everyone tracked was something called the triple product, the product of plasma density, temperature, and confinement time. You need all three to be high simultaneously to get net fusion energy. Think of it like trying to start a campfire. You need enough fuel packed together. It needs to be hot enough to ignite, and you need to keep it hot long enough for the fire to catch and sustain itself. If any one of those three is too low, you don't get a fire. For fusion, the specific target is called the Lawson criterion, named after John Lawson, a British engineer who worked it out in 1955, though his report was classified for 2 years because, well, everything was classified back then. Lawson calculated that for a deuterium-tritium plasma, you need the triple product to exceed a certain threshold for the fusion energy produced to exceed the energy you're pumping in to keep the plasma hot. That threshold is roughly density times temperature times confinement time needs to be greater than about 3 times 10 to the 21 in units of kilo-electron-volts per cubic meter per second, if you want to be precise about it, though the exact number depends on how you define your terms. What matters is that through the 70s, each new tokamak pushed the triple product higher. The progress was actually quite impressive when you plotted it on a graph, roughly doubling every couple of years, a pace that people sometimes compared to Moore's law in computing. And this progress bred a new wave of optimism. Maybe fusion really was just around the corner. Maybe with one more generation of machines, you could reach break-even, the point where the fusion reactions produce as much energy as you put in. But here's the thing about plasma physics, and this is something you start to appreciate the more you study it. The plasma always has another trick up its sleeve. As the machines got bigger and hotter, new instabilities appeared that hadn't been important in smaller devices. Edge-localized modes, or ELMs, which are periodic bursts of energy that erupt from the plasma edge and can damage the walls of the machine. Disruptions, where the plasma current suddenly collapses and dumps all its energy into the vessel wall in milliseconds, generating enormous mechanical forces that can literally shake the machine apart. Neoclassical tearing modes, which create magnetic islands inside the plasma that degrade confinement. Each of these required new understanding, new control techniques, new engineering solutions. And then there was the question of materials. Even if you solve the plasma physics, you still have to build a machine that can survive in the environment a fusion reactor creates. And this is where the engineering gets really, really hard. A working fusion reactor would produce enormous fluxes of high-energy neutrons, 14.1 mega-electron-volt neutrons from the deuterium-tritium reaction, which are far more energetic than the neutrons produced in fission reactors. These neutrons slam into the walls and structural materials of the reactor, displacing atoms from their crystal lattices, creating defects, making the material swell and become brittle over time. The technical term is radiation damage, and it's measured in displacements per atom, how many times, on average, each atom in the material has been knocked out of its position. In a fusion power plant, the structural materials near the plasma might experience 20 to 30 displacements per atom per year. That's an extraordinary amount of damage. It means that over the lifetime of the reactor, every atom in the wall material has been displaced from its original position dozens of times. Finding materials that can withstand this punishment while maintaining their structural integrity, while not becoming too radioactive themselves, while being compatible with the coolant, while being manufacturable at industrial scale, that's one of the grand materials science challenges of our time, and it's still not fully solved. But in the 1970s, the focus was still primarily on the plasma physics, on proving that you could reach the temperatures and confinement times needed for fusion. The materials problem was acknowledged, but deferred, a problem for the next generation. And the next generation was already being planned. By the late 70s, the fusion community was designing what they hoped would be the machine that finally demonstrated break-even and beyond. In the United States, that machine was called TFTR, the Tokamak Fusion Test Reactor, built at Princeton and designed to be the first machine to use actual deuterium-tritium fuel, not just deuterium. In Europe, JET was under construction with similar ambitions. And in the background, conversations were beginning about something even bigger, an international machine that would go beyond break-even and actually produce significant amounts of fusion power. Those conversations would eventually lead to one of the most ambitious and complicated engineering projects in human history. But that story was still years away from taking shape. What mattered in the moment was TFTR, which started operating in 1982, and the extraordinary series of experiments it would run over the next decade or so. And what a decade it was. TFTR was a big machine. The plasma chamber had a major radius of about 2.5 meters, and the whole device weighed thousands of tons when you counted the magnets, the shielding, the support structure, all of it. Princeton had been at the center of American fusion research since Lyman Spitzer started the Stellarator program back in the 50s, and TFTR represented the culmination of everything they'd learned. The whole point of the machine was right there in the name. This was a test reactor, and the test was whether you could actually burn deuterium-tritium fuel in a tokamak and get meaningful amounts of fusion power out. But here's the thing. They didn't jump straight to DT fuel. For the first several years, TFTR ran on plain deuterium, which is much easier to handle because it doesn't involve tritium. And tritium, you should know, is a whole headache unto itself. It's radioactive with a half-life of about 12.5 years. It decays by emitting a beta particle, a fast electron. And while that radiation isn't terribly penetrating, tritium is dangerous if you inhale it or ingest it because it's chemically identical to ordinary hydrogen. It bonds into water molecules, gets absorbed into your body, and irradiates you from the inside. So working with tritium means building elaborate containment systems, glove boxes, air handling systems that can capture any tritium that escapes, decontamination procedures, the whole 9 yards. It adds enormous complexity and cost to any experiment. So for years, TFTR operated with deuterium-only plasmas, and even those experiments were incredibly productive. The machine achieved record plasma temperatures, explored different heating schemes. They used neutral beam injection, where you accelerate beams of neutral atoms to high energy and shoot them into the plasma, transferring their kinetic energy to the plasma particles through collisions. TFTR's neutral beams were powerful, eventually reaching about 40 megawatts, which is a tremendous amount of heating power being dumped into a volume of gas that weighs less than a postage stamp. Think about that. 40 million watts of power going into something that weighs maybe a fraction of a gram. The temperatures you can reach with that kind of power density are extraordinary. And during this same period, jet was coming online across the Atlantic. The Joint European Torus, JET, was built at Culham in England, which is fitting because that's where the old Zeta machine had been, the one that had made those premature claims about fusion back in 1958. JET was actually bigger than TFTR, with a major radius of about 3 meters, and it was designed from the start with a D-shaped plasma cross-section rather than a circular one. This might sound like a minor geometric detail, but it turned out to be really important. A D-shaped plasma can carry more current and achieve higher pressure for a given magnetic field strength, which means better confinement. The physics behind this involves something called the Shafranov shift and the way plasma pressure interacts with the magnetic geometry, but the practical upshot is that elongated, D-shaped plasmas became the standard for all serious tokamaks after JET demonstrated the advantages. JET also pioneered something called the diverter configuration, where the magnetic field lines at the edge of the plasma are deliberately shaped to guide escaping particles and heat to specific target plates rather than letting them hit the wall wherever they please. This gives you much better control over impurities, those stray atoms of wall material that contaminate the plasma and radiate away its energy. The diverter was a genuine breakthrough in plasma engineering, and it's now considered essential for any reactor-scale tokamak. Now, there was a friendly but real rivalry between TFTR and JET throughout the 80s and into the 90s. Both teams were pushing toward the same goal, demonstrating significant fusion power from DT fuel, and both wanted to get there first. The Americans at Princeton had the advantage of being specifically designed for DT from the beginning, with all the tritium handling infrastructure built in. JET had the advantage of being bigger and having the more advanced plasma shape. The Japanese were in the race too, with their JT60 machine, which was comparable in size but wasn't designed to handle tritium, so it couldn't do actual DT experiments. Instead, JT60 focused on achieving the plasma conditions that would produce break-even if you were using DT fuel, a kind of extrapolated break-even, calculated rather than measured directly. The competition drove both teams to push harder, and through the late 80s, records kept falling. Higher temperatures, longer confinement times, better triple products. The Lawson criterion was getting closer, but the real prize was actual DT operation, and TFTR got there first. On December 9, 1993, TFTR produced its first deuterium-tritium plasma, and it worked. The machine generated about 6 megawatts of fusion power. 6 megawatts from actual thermonuclear fusion reactions in a magnetically confined plasma. Now, to be clear, the machine was consuming far more power than it produced. The neutral beams alone were pumping in around 40 megawatts, and that's not even counting the power to run the magnets and all the other systems. So this was nowhere near break-even, in any practical sense. But it was real fusion power, measurable and significant, and it proved that the physics worked the way everyone had calculated it would. Here's what's really clever about how they confirmed the fusion was happening. When deuterium and tritium fuse, they produce a helium-4 nucleus, an alpha particle, carrying 3.5 mega-electron volts of energy, and a neutron carrying 14.1 mega-electron volts. Those neutrons are a dead giveaway. You can detect them outside the machine with neutron counters, and the number and energy of the neutrons tells you exactly how many fusion reactions are occurring. It's an unambiguous signal. There's no way to fake it, no way to misinterpret it the way Zeta's results had been misinterpreted decades earlier. The neutrons don't lie. TFTR went on to set records over the following months, eventually reaching about 10.7 megawatts of fusion power in 1994. That was the peak. 10.7 megawatts from a single pulse. It's a number that might not sound like much in a world where a single large power plant produces 1,000 megawatts. But remember, this was a physics experiment, not a power plant. The point was to demonstrate the science, and the science was working. Then JET answered. In 1997, JET conducted its own DT campaign and achieved about 16 megawatts of peak fusion power. More importantly, JET achieved a Q value, the ratio of fusion power out to heating power in, of about 0.67. That means for every watt of heating power they put into the plasma, they got back about 2/3 of a watt in fusion power. Still below break-even, still below Q equals 1, but remarkably close. And the plasma behavior matched theoretical predictions well enough that physicists were confident. A bigger machine, with stronger magnets and better confinement, could get past break-even and into the regime where the alpha particles from the fusion reactions themselves provide most of the heating. That's called a burning plasma, and it's the holy grail of fusion research, a plasma that sustains its own temperature primarily through its own fusion reactions, with external heating only needed for control and fine-tuning. JET's 1997 record of 16 megawatts still stands, by the way. As of the time I'm telling you this, no machine has surpassed it. JET held that record for over 25 years. That tells you something about the pace of progress, or rather, the pace at which funding and political will have allowed progress to happen. But we'll get to that. Let me take a step back and talk about what was happening politically, because the politics of fusion are almost as complicated as the physics. In the mid-1980s, at the Geneva Summit in 1985, Ronald Reagan and Mikhail Gorbachev agreed to pursue an international fusion project together. This was remarkable. At the height of the Cold War, the two superpowers agreed that fusion energy was important enough to collaborate on. The project was called ITER, which originally stood for International Thermonuclear Experimental Reactor, though later the organization quietly stopped using the acronym and just called it ITER, which also happens to be the Latin word for the way. Europe, Japan, and eventually other partners joined. The idea behind ITER was straightforward in concept. Build a tokamak big enough to achieve Q equals 10 times more fusion power out than heating power in, and sustain a burning plasma for hundreds of seconds. Not a power plant, but a demonstration that sustained, high-gain fusion is physically possible at a scale relevant to energy production. ITER would have a major radius of about 6.2 meters, roughly twice the size of JET, with superconducting magnets that could run indefinitely, rather than the copper magnets used in TFTR and JET that could only pulse for a few seconds before overheating. But here's where things got complicated. Designing ITER took years. Then redesigning it took more years. The original design from the early 90s was enormous and expensive, and when the cost estimates came in, some partners balked. The United States actually pulled out of the project in 1998, partly over cost concerns and partly due to shifting political priorities. They rejoined in 2003, but the gap cost precious time. The design was scaled back somewhat to reduce costs, though it was still the most expensive scientific instrument ever proposed. The site selection process was its own political drama. Japan and France both wanted to host the machine, and the debate dragged on for years. France eventually won, and the site chosen was Cadarache in the south of France, near Aix-en-Provence. Construction formally began around 2010, though site preparation work started earlier. And then the delays began. ITER is not just a physics project, it's an engineering project of staggering complexity, and it involves 7 major partners: the European Union, the United States, Russia, Japan, South Korea, China, and India. Each partner contributes specific components manufactured in their own countries, which then have to be shipped to France and assembled with nanometer-level precision. The logistics alone are mind-bending. Some of the components are so large they required special roads to be built just to transport them from the Mediterranean port to the construction site. The tokamaks vacuum vessel, for instance, is made of 9 sectors, each weighing about 440 tons, manufactured in different countries, and shipped to Cataract for welding together. The superconducting magnets use niobium tin and niobium titanium conductors cooled to 4 Kelvin, 4 degrees above absolute zero, and the toroidal field coils are among the most powerful superconducting magnets ever built, each one about 17 meters tall. The precision required in manufacturing and assembling these components is extraordinary, and when you're coordinating work across 7 different partners with different engineering standards, different manufacturing cultures, different quality control systems, well, you can imagine the challenges. Cost estimates for ITER have grown dramatically over the years, from initial projections of around $5 billion to current estimates that are several times that. The schedule has slipped repeatedly. First plasma, originally expected around 2016, was pushed to 2025. Then later, and the DT operation phase has been pushed out further still. ITER has become, for some critics, a symbol of everything that's wrong with big government science projects. Too slow, too expensive, too bureaucratic. For its defenders, it remains the only credible path to demonstrating that fusion can work at reactor scale, and the delays, while painful, are the inevitable cost of doing something that has never been done before at this level of complexity. But while ITER was slowly taking shape in the south of France, something unexpected was happening elsewhere. A new generation of fusion projects was emerging, driven not by governments, but by private companies, funded by venture capital and billionaire investors who believed that fusion could be achieved faster and cheaper than the traditional big science approach. And some of these companies were pursuing radically different approaches to the problem, not just incremental improvements on the tokamak, but entirely new confinement concepts that the mainstream fusion community had set aside decades earlier. The story of private fusion is fascinating and contentious, and it really starts to pick up steam in the 2010s. But the seeds were planted earlier than that, actually, going back to the late 1990s and early 2000s, when a handful of visionaries, some of them physicists, some of them entrepreneurs, some of them a little bit of both, started asking a dangerous question. What if the tokamak isn't the only way? What if it's not even the best way? Now, to understand why that question was so dangerous, you have to appreciate how deeply the tokamak had become entrenched as the default approach. By the 1990s, decades of research, billions of dollars, entire careers had been built around the tokamak concept. The international community had essentially bet everything on it with ITER. And the tokamak had earned that position. It genuinely produced the best plasma confinement results, the highest temperatures, the longest confinement times. But there was a nagging problem. Tokamaks kept getting bigger and more expensive. The progression from small university experiments to TFTR to JET to ITER followed a trajectory that, if you extended it forward, suggested that a commercial fusion power plant based on a tokamak might need to be enormous and enormously expensive. And if the first commercial fusion plant costs $30 or $50 billion, well, that's not really a viable energy technology, is it? You can build a lot of solar panels and wind turbines for that kind of money. So the question became, is there a way to make fusion smaller, simpler, cheaper? And a few people started to think seriously about that. One of the earliest was a company called Tri-Alpha Energy, founded in 1998, later renamed TAE Technologies. The company was built around the ideas of Norman Rostoker, a physicist at UC Irvine who had spent decades thinking about an alternative confinement concept called the field reversed configuration, or FRC. An FRC is a beautiful thing. Conceptually, imagine a plasma that generates its own magnetic field, a self-contained magnetic bottle where the plasma essentially holds itself together. No giant external magnets needed, or at least far fewer of them. Rostoker believed that if you could get an FRC hot enough and stable enough, you could build a fusion reactor that was far more compact than a tokamak. And here's the thing, he wasn't just some fringe thinker. He was a deeply respected plasma physicist, with decades of serious theoretical work behind him. He attracted serious money, including early investment from Paul Allen, the Microsoft co-founder. Then there was General Fusion, founded in 2002 in Vancouver by Michel Laberge, a physicist who had been working in the laser printing industry and basically couldn't stop thinking about fusion. Laberge's approach was completely different. Magnetized target fusion, which is sort of a hybrid between magnetic confinement and inertial confinement. The idea is that you create a compact magnetized plasma, then physically compress it using pistons, actual mechanical pistons, to reach fusion conditions. It sounds almost steampunk, doesn't it? Like someone decided to build a fusion reactor in a Victorian workshop. But the physics is sound, at least in principle. You're using the magnetic field to insulate the plasma so it doesn't lose its heat to the walls during compression, and you're using mechanical compression to achieve the density and temperature you need. It's clever because it potentially avoids the need for both the giant magnets of a tokamak and the giant lasers of inertial confinement. But the company that really changed the conversation, the one that made the mainstream fusion community sit up and take notice, was Commonwealth Fusion Systems, or CFS, which spun out of MIT in 2018. And the story of CFS is really the story of a technological breakthrough that had nothing to do with plasma physics at all. It was about magnets. Here's the thing about tokamaks. The strength of the magnetic field is everything. The stronger your magnetic field, the better you can confine the plasma, and the smaller your machine can be. This is a direct physical relationship. The fusion power density scales with the fourth power of the magnetic field strength. The fourth power. That means if you double the magnetic field, you get 16 times the fusion power in the same volume. Or, looked at another way, you can get the same fusion power in a machine that's dramatically smaller. For decades, tokamaks used copper electromagnets, or low-temperature superconducting magnets made from niobium tin or niobium titanium alloys. These materials have fundamental limits on how strong a field they can produce. ITER's magnets, for instance, use niobium tin superconductors cooled to 4 degrees above absolute zero, and they can produce a toroidal field of about 12 Tesla on the conductor. That's very strong, but it's close to the material's limit. Now, starting in the 2000s, a new class of superconducting materials became increasingly available. High-temperature superconductors, specifically a material called ReBCO, which stands for rare earth barium copper oxide. These are tape-like conductors, thin and flexible, and they can carry enormous currents in very strong magnetic fields. They're called high-temperature superconductors, not because they operate at room temperature. They still need to be cooled to around 20 Kelvin, which is minus 253 Celsius. But because that's much warmer than the 4 Kelvin that conventional superconductors require. And crucially, Rebecco tapes can produce much stronger magnetic fields than niobium tin. We're talking about fields of 20 Tesla or more on the conductor. A group at MIT, led by Dennis White, who ran the Plasma Science and Fusion Center, realized that Rebecco magnets could be transformative for fusion. If you could build a tokamak with a 20 Tesla magnet instead of a 12 Tesla magnet, the fourth power scaling meant you could build a machine that was vastly smaller and cheaper than ITER, but achieved similar, or even better, plasma performance. They called their concept Spark. It was designed to be a compact, high-field tokamak with a major radius of about 1.85 meters. Compare that to ITER's 6.2 meters. Spark was designed to achieve Q greater than 2, meaning it would produce more than twice as much fusion power as the heating power put in a machine you could practically fit in a large gymnasium. Commonwealth Fusion Systems was founded to commercialize this idea, and they attracted enormous investment, over $2 billion by the early 2020s, from investors including Breakthrough Energy Ventures, which is Bill Gates's climate-focused fund, and the Italian energy company Eni. In September 2021, CFS successfully tested a full-scale Rebecco magnet that achieved a field of 20 Tesla, making it the strongest high-temperature superconducting magnet of its kind ever built. That test was a genuine milestone. It demonstrated that the enabling technology for a compact, high-field tokamak actually worked. It wasn't just theoretical anymore, and CFS wasn't alone. By the early 2020s, there were more than 30 private fusion companies worldwide, collectively attracting billions of dollars in investment. You had Helion Energy in Everett, Washington, pursuing a pulsed approach using field-reversed configurations that collide at high speed. Their concept involves compressing the merged plasma magnetically and actually extracting energy directly from the changing magnetic field, which would bypass the need for a traditional steam turbine entirely. That's a wild idea. You had Zap Energy, also in the Seattle area, working on sheared flow stabilized Z-pinches, a concept that uses the plasma's own flowing motion to stabilize what would otherwise be a hopelessly unstable pinch. You had First Light Fusion in Oxford, England, pursuing a projectile-based inertial fusion approach, where they literally fire a projectile at a target to create the conditions for fusion, like a tiny, precisely engineered collision. Each of these companies was making a bet that a different approach to the problem could work, and that by operating as a private company, lean, fast, focused, they could move more quickly than the ponderous international ITER collaboration. And there's something genuinely exciting about this moment. For the first time in the history of fusion research, there was real competition. Not just between national labs, but between fundamentally different technical approaches, each backed by people who had real money on the line and real urgency to show results. But let's be honest about the challenges, because they're enormous. Every one of these companies faces the same fundamental physics that has made fusion so hard for 70 years. You still have to confine a plasma at 100 million degrees. You still have to deal with instabilities. You still have to find materials that can withstand the neutron bombardment from DT fusion, 14.1 mega-electron-volt neutrons that will damage and activate any material they hit. You still have to breed tritium. You still have to extract heat and convert it to electricity reliably, day after day, year after year. A proof of concept in a laboratory is one thing. A power plant that runs 24/7 for 30 years, competing economically with solar and wind and batteries and fission and natural gas, that's something else entirely. And this brings us to something important that doesn't get talked about enough in the breathless coverage of private fusion: the materials problem. Think about what the first wall of a fusion reactor has to endure. It's facing a plasma at 100 million degrees. It's being bombarded by high-energy neutrons that knock atoms out of their crystal lattice positions, creating defects, making the material swell and become brittle. It's being hit by helium atoms that get implanted in the surface and form bubbles. It's experiencing enormous heat fluxes. In the diverter region, where the exhaust plasma strikes the wall, the heat load can be 10 megawatts per square meter or more, which is comparable to the heat flux at the surface of the sun. And all of this is happening in the presence of strong magnetic fields, mechanical stresses, and, if you're using tritium, a radioactive fuel that's notoriously difficult to contain because it's so small it can diffuse through solid metal. The leading candidate material for the first wall and blanket structure is a type of steel called RAFM, reduced activation ferritic martensitic steel, specifically a variant called Eurofur. It's been engineered to avoid elements like nickel, molybdenum, and niobium that would become highly radioactive under neutron irradiation. Instead, it uses tungsten and tantalum as alloying elements. The idea is that after a fusion reactor is decommissioned, the structural materials would become low-level waste that could be recycled after 100 years or so, rather than remaining dangerously radioactive for thousands of years, like fission waste. That's a genuine advantage of fusion over fission, by the way. The fuel itself produces no long-lived radioactive waste. The radioactivity comes entirely from neutron activation of the structural materials, and by choosing those materials carefully, you can minimize the long-term waste problem dramatically. But here's the thing. Nobody has ever tested these materials under realistic fusion neutron conditions for extended periods, because no fusion device has ever run long enough or produced enough neutrons to do a proper test. This is one of the key reasons why a facility called IFMIF, the International Fusion Materials Irradiation Facility, has been proposed. It would use particle accelerators to produce a beam of neutrons with the same energy spectrum as DT fusion neutrons, and you'd use that beam to irradiate material samples for years, simulating decades of exposure inside a reactor. A smaller prototype called IFMIF-DONES is being built in Granada, Spain, but it won't be operational for some years yet. So we're in this strange situation where we're designing power plants that depend on materials whose long-term behavior under fusion conditions we haven't fully characterized. It's like designing an airplane engine using an alloy you've never actually tested at operating temperature. And then there's the tritium question, which is maybe the most underappreciated challenge in all of fusion energy. Tritium is radioactive, with a half-life of about 12.3 years. It doesn't exist in significant quantities in nature. The world's entire supply of tritium is only about 25 kilograms, and most of it is produced as a byproduct of heavy water fission reactors, specifically the CANDU reactors in Canada and a few others. A commercial fusion power plant would burn something like 55 kilograms of tritium per year for each gigawatt of electrical output. So the existing global supply wouldn't even fuel a single large power plant for a year. The plan has always been that fusion reactors would breed their own tritium, using lithium in the blanket surrounding the plasma. When a 14 megavolt neutron hits a lithium-6 atom, it produces tritium and helium. The reaction actually releases energy, which is a nice bonus, but you need to capture essentially every neutron, breed slightly more than one tritium atom per fusion reaction to account for losses, extract the tritium from the blanket, purify it, and feed it back into the plasma, all continuously, all reliably, all while handling a radioactive gas that can permeate through metal walls and is hazardous in even tiny quantities. Nobody has ever demonstrated a complete tritium breeding cycle in a fusion device. ITER will test several different blanket module designs. They're called test blanket modules, but even ITER won't operate with a full breeding blanket. The first machine that will need to actually close the tritium fuel cycle will be a demonstration power plant, sometimes called DEMO, which various countries are planning as the step after ITER. And this is where the engineering gets really, really hard, because you're not just doing plasma physics anymore. You're doing nuclear engineering, chemical engineering, materials science, remote handling robotics, because everything inside the reactor becomes radioactive and has to be maintained by robots. And you're doing all of it simultaneously in an integrated system where everything affects everything else. This is actually one of the strongest arguments for the private fusion companies, some of which are pursuing aneutronic or low-neutron fusion reactions that would sidestep many of these materials and tritium challenges. Helion Energy, for instance, is ultimately targeting the fusion of deuterium with helium-3, a reaction that produces a proton instead of a neutron. No neutron means dramatically less radiation damage to the reactor structure, no need for tritium breeding, and the possibility of direct energy conversion, capturing the kinetic energy of the charged fusion products directly as electricity, without the intermediate step of heating water and driving a steam turbine. The catch is that deuterium-helium-3 fusion requires even higher temperatures than DT fusion, roughly 6 times higher, and helium-3 is extremely rare on Earth, though it's more abundant on the Moon, which opens up a whole other conversation about lunar mining that sounds like science fiction, but is actually being seriously discussed. TAE Technologies is also pursuing a non-DT fuel cycle, specifically proton-boron-11 fusion, which produces 3 helium nuclei and no neutrons at all. But proton-boron fusion requires temperatures of about 3 billion degrees, billion with a B, which is roughly 200 times hotter than the core of the sun. And just let that sit for a moment. 200 times hotter than the center of a star. The plasma physics required to sustain those conditions is extraordinarily demanding, and no one has achieved anything close to net energy from proton-boron fusion yet. but TAE has been methodical about it. They've built a series of machines, Norman, named after their late founder Norman Rostocker, and more recently, Copernicus. Each one pushing their field-reversed configuration plasma to higher temperatures and longer confinement times. Their roadmap envisions an intermediate step using deuterium-tritium or deuterium-helium-3 before eventually reaching proton-boron, and they've attracted significant investment, over $1 billion. Partly because if you could actually make proton-boron work, you'd have a reactor that produces almost no radioactive waste, needs no tritium breeding, and could potentially be far simpler and cheaper than anything based on DT fusion. That's a big if. But it's a beautiful if. And this is something worth pausing on, because it reveals a really interesting tension in the fusion world right now. On one side, you have the mainline approach, ITER, the big national labs, the established tokamak programs, all converging on deuterium-tritium fusion because it's the easiest fusion reaction to achieve. DT has the highest cross-section at the lowest temperature. It's the path of least resistance, thermodynamically speaking. But it comes with all those engineering headaches we talked about, the neutron damage, the tritium breeding, the activated materials, the remote handling. On the other side, you have these private ventures saying, what if we skip all that complexity by going after a harder plasma physics problem, but an easier engineering problem? What if the real shortcut is to aim higher in temperature, but lower in system complexity? Neither side is obviously right. And honestly, that's kind of exciting. Because for the first time in fusion's history, there are genuinely different bets being placed, different philosophies being tested in parallel, with real money behind them. For decades, fusion research was essentially a single-track affair, government-funded, tokamak-dominated, incremental. Now, it's a portfolio. And portfolios, historically, are how breakthrough technologies actually get developed. You don't know which approach will work until someone builds it and turns it on. So let's talk about what's actually being built right now, because the landscape, as of the early 2020s, is unlike anything fusion has ever seen. There are over 40 private fusion companies worldwide, collectively backed by tens of billions of dollars in investment. Some of them are building real hardware, not just doing simulations or writing papers, but pouring concrete and bending steel and commissioning magnets. Commonwealth Fusion Systems, CFS, is probably the furthest along among the private tokamak ventures. After that landmark demonstration of their 20 Tesla Rebeco magnet in September 2021, they moved into construction of Spark at a site in Devens, Massachusetts. Spark is designed to be relatively compact. Remember, that major radius of about 1.85 meters, which is tiny compared to ITER's 6.2 meters. But because of those incredibly powerful high-temperature superconducting magnets, it should achieve a magnetic field strength of about 12 Tesla on axis. And here's where that fourth power scaling law really pays off. Fusion power scales roughly as the fourth power of the magnetic field strength, so doubling the field gives you 16 times the fusion power for the same plasma volume. That's why Spark can be so much smaller than ITER, while still aiming for a Q greater than 2, meaning it would produce more than twice as much fusion power as the heating power pumped in. If it works, It would be the first controlled fusion experiment to produce a significantly burning plasma. A plasma where the energy from the fusion reactions themselves is the dominant source of heating, not the external systems. CFS has said they're targeting first plasma in the mid-2020s, though timelines in fusion have a well-earned reputation for slipping. Their longer-term plan is a commercial pilot plant called ARC, which would actually generate electricity and feed it to the grid. Helion Energy, meanwhile, has been building their 7th-generation machine called Polaris at a facility in Everett, Washington. Helion's approach is genuinely different from a tokamak. They create 2 compact toroids of plasma, field-reversed configurations, accelerate them toward each other at high speed, and collide them. The collision compresses the plasma to fusion conditions, and then here's the clever part. As the fused plasma expands, it pushes against the magnetic field, and that changing magnetic flux induces a current directly in the surrounding coils. It's essentially the reverse of how you heat the plasma. Instead of putting electrical energy in and getting plasma heating out, you're putting fusion energy in and getting electrical energy out. Direct energy conversion. No steam, no turbines, no cooling towers. Helion signed a power purchase agreement with Microsoft in 2023, committing to deliver fusion electricity by 2028. That's an extraordinarily ambitious timeline, and plenty of physicists are skeptical. But the fact that a company like Microsoft is willing to put a contract on it tells you something about how the commercial landscape has shifted. Then, there's the inertial confinement side, which we haven't talked about as much. But something remarkable happened in December 2022 at the National Ignition Facility, NIF, at Lawrence Livermore National Laboratory in California. NIF uses the world's most powerful laser system, 192 laser beams that converge on a tiny capsule of deuterium-tritium fuel, about the size of a peppercorn, housed inside a gold cylinder called a hohlraum. The lasers deliver about 2 megajoules of ultraviolet light in a few billionths of a second, which heats the hohlraum walls until they emit a bath of X-rays, which in turn compress the fuel capsule so rapidly and symmetrically that it implodes, reaching temperatures and densities where fusion ignites. It's called indirect drive because the lasers don't hit the fuel directly. They hit the hohlraum, and the X-rays do the actual compression. On December 5th, 2022, NIF fired a shot that delivered 2.05 megajoules of laser energy to the target and got back 3.15 megajoules of fusion energy, more energy out than laser energy in. For the first time in history, a controlled fusion experiment had achieved ignition, scientific energy gain, in the laboratory. The announcement made headlines around the world, and rightfully so. It was a genuine milestone, decades in the making. But here's the thing, and this is important to understand. NIF's achievement, while historic, doesn't directly translate to a power plant. The 2.05 megajoules of laser energy that hit the target required about 300 megajoules of electrical energy to produce, because the lasers are only about 1% efficient. So the overall energy balance, wall plug to wall plug, was still deeply negative, and NIF was designed primarily as a weapons physics facility, not as an energy research machine. Its lasers can only fire a few times a day at most, whereas a laser fusion power plant would need to implode something like 10 fuel capsules per second, every second, around the clock. The engineering gap between what NIF demonstrated and a working power plant is enormous. Still, the physics validation matters. It proves that the fundamental concept works. You can compress fuel to the point where fusion reactions release more energy than you put in, and several companies are working on the engineering side of inertial fusion energy. We mentioned First Light Fusion earlier, the Oxford-based company using projectile impact instead of lasers. There's also Focused Energy in Germany and the US, and Excimer Energy, which is developing a much more efficient laser architecture specifically designed for high repetition rate fusion. Now, let's step back and think about what all of this means in the bigger picture. Because fusion isn't happening in a vacuum. No pun intended. It's happening in the context of a global energy transition that's already underway. Solar and wind power have gotten dramatically cheaper over the past 2 decades. Battery storage is improving rapidly. Fission nuclear power, despite its political challenges, is experiencing a resurgence of interest, with new small modular reactor designs being developed in several countries. So the question that fusion has to answer isn't just, can we make it work? But can we make it work soon enough and cheaply enough to matter? And this is where the conversation gets really interesting, because fusion has some characteristics that no other energy source can match. It's energy dense beyond anything else available. A single kilogram of fusion fuel, a roughly 50-50 mix of deuterium and tritium, releases about the same energy as 10 million kilograms of coal. The fuel is essentially inexhaustible. Deuterium can be extracted from seawater, and there's enough of it to power civilization for billions of years. Fusion produces no greenhouse gases during operation. It produces no long-lived radioactive waste. The activated structural materials from a DT reactor would need to be stored for perhaps 100 years, not hundreds of thousands of years like spent fission fuel. And a fusion reactor can't melt down. If you lose control of the plasma, it just cools off and stops. There's no chain reaction to run away. The physics is inherently self-limiting. These are genuinely remarkable properties, and they matter most in the scenarios that are hardest for other clean energy sources to address. Think about industrial heat, steel production, cement manufacturing, chemical processing, where you need enormous amounts of very high-temperature thermal energy that's hard to provide with intermittent renewables. Think about dense urban centers in countries that don't have abundant wind or solar resources. Think about marine shipping, or eventually, space propulsion. Fusion occupies a niche that's potentially enormous, even in a world that's already deploying solar and wind at scale. But the honest truth is that none of this matters if the engineering doesn't come together. And the engineering challenges we've been talking about throughout this story. Materials that can withstand the neutron bombardment, magnets that can sustain the fields, plasma control systems that can manage the instabilities, tritium breeding systems that can close the fuel cycle, and all of it integrated into a machine that can run reliably for years at a time. These are not solved problems. They're problems being actively worked on by thousands of very smart people around the world with more resources than ever before. But they're still open problems. And there's one more piece of this puzzle that doesn't get talked about enough, which is the regulatory and licensing framework. How do you license a fusion power plant? What safety standards apply? Fusion isn't fission. The risk profile is fundamentally different. But in many countries, the regulatory frameworks haven't caught up to that reality. In the United States, the Nuclear Regulatory Commission announced in 2023 that it would regulate fusion machines under a framework more similar to particle accelerators than to fission reactors, which was widely seen as a positive step by the fusion industry. The United Kingdom has taken a similar approach through its Fusion Energy Act. But in other jurisdictions, the regulatory picture is still developing, and in some cases it's genuinely unclear whether fusion plants will be classified alongside nuclear fission reactors with all the regulatory burden that entails, or whether they'll be treated as something fundamentally new. In the European Union, for instance, there's been ongoing discussion about how the Euratom Treaty applies to fusion, and different member states have taken different positions. France, which hosts ITER, has its own regulatory approach through the Autorité de Sûreté Nucléaire, and the classification of ITER itself has involved years of negotiation about safety standards. Japan, South Korea, China. Each of these countries has a growing fusion program, and each is working through its own version of this question. And it matters enormously because regulatory uncertainty can add years and billions of dollars to a project timeline. And for the private companies racing to build the first commercial fusion plant, knowing what rules they'll need to follow is almost as important as solving the physics. So let's step back for a moment and think about where we actually are in this story. Because we've covered a lot of ground together, and I think it's worth just quietly taking stock of how far humanity has come on this particular journey. A little over a century ago, nobody knew why the sun shone. That's it. That's where we started. People looked up at the sky and saw this impossibly bright, impossibly hot thing. And the best scientific minds of the 19th century couldn't explain it. Lord Kelvin calculated that if the sun were burning coal, it would have exhausted its fuel in a few thousand years. Helmholtz proposed gravitational contraction, which bought you maybe 20 million years, but geologists were already saying the Earth was far older than that. There was this genuine, deep mystery at the heart of everything, the source of all energy on Earth, the thing that makes life possible, and nobody could explain where it came from. And then, in this astonishing cascade of discoveries over just a few decades, Röntgen finding X-rays, Becquerel stumbling onto radioactivity, the Curies isolating radium, Einstein writing down E equals mc squared on what was essentially a theoretical hunch, Rutherford working out the structure of the atom, Aston measuring the mass defect, Eddington making the audacious leap that stars must be converting hydrogen into helium. In this rush of insight, humanity figured out the answer. The sun is a fusion reactor. It's taking the lightest element in the universe and squeezing it together so hard that it becomes something else. And the tiny difference in mass between what goes in and what comes out is released as energy. And that energy is what warms your face on a summer afternoon. That understanding, that chain of reasoning from pure curiosity to fundamental insight, is one of the great achievements of the human mind. And then came the harder question. can we do it ourselves? Can we recreate what the sun does here on Earth in a controlled way and use it to power civilization? The first time we released fusion energy on Earth, it was in a weapon. The Ivy Mike test, November 1952. Eniwetok Atoll, a fireball 3 miles wide. That's a moment worth sitting with, because it tells you something important about the relationship between understanding and application. We understood fusion well enough to destroy with it long before we understood it well enough to build with it. The physics of a thermonuclear weapon is, in a certain terrible sense, simpler than the physics of a fusion power plant, because in a weapon, you don't need to sustain the reaction. You just need to start it. The confinement is provided by the inertia of the fuel itself. Everything happens so fast that the fuel doesn't have time to fly apart before a significant fraction of it fuses. But in a power plant, you need the reaction to keep going, steadily, controllably, for months and years. And that turns out to be extraordinarily difficult. We've talked about why. The plasma is 10 times hotter than the core of the sun. It's a roiling, turbulent, electrically charged gas that wants to expand, wants to cool, wants to touch the walls of whatever you put it in. And if it does touch those walls, it erodes them and poisons itself with impurities. Containing it with magnetic fields is like trying to hold water in a net made of rubber bands. The plasma finds every weakness, every asymmetry, every tiny imperfection in the field, and exploits it. The instabilities have names that sound almost whimsical: kink modes, sausage modes, ballooning modes, edge-localized modes. But each one represents a real physical phenomenon that can dump the plasma's energy onto the reactor wall in milliseconds. And yet, despite all of that, the progress has been real. The Lawson criterion, that benchmark for how hot and dense and well-confined the plasma needs to be, has been approached and in some measures exceeded. JET produced 16 megawatts of fusion power. The National Ignition Facility achieved ignition, more energy out of the fuel than went into it. ITER, for all its delays and cost overruns, is the most sophisticated scientific instrument ever constructed, and when it operates with deuterium-tritium fuel, it's designed to produce 10 times more fusion power than the heating power injected into the plasma. The superconducting magnets, the cryogenic systems, the plasma-facing components, the diagnostic instruments. Each one of these is a marvel of engineering in its own right. And now there's this whole new ecosystem of private companies, dozens of them, funded by billions of dollars of private capital, each pursuing a different approach, each convinced they've found a shortcut or an improvement or a fundamental insight that the big government programs missed. Commonwealth fusion systems, with their high-temperature superconducting magnets, building Spark in Devens, Massachusetts, aiming for a compact, high-field tokamak that could demonstrate net energy gain. Helion, up in Everett, Washington, with their pulsed field-reversed configuration approach and that power purchase agreement with Microsoft for 2028, a date that, honestly, most physicists I've talked to consider extremely ambitious. But the fact that a company like Microsoft is willing to sign that agreement tells you something about the seriousness of the effort. TAE Technologies, pursuing proton-boron-11 fusion, which is harder physics but cleaner engineering. Zap Energy, trying to make the Z-pinch work with sheared flows. First Light Fusion, shooting projectiles at fuel targets, each one a different bet on which combination of physics and engineering will get there first. Here's what I find genuinely moving about all of this. It's the sheer persistence. Fusion has been 30 years away for so long that it's become a punchline. And there's a real critique embedded in that joke. The timelines have repeatedly slipped, the costs have repeatedly escalated, and promises have been made that weren't kept. But the reason the timeline slipped wasn't that the physics was wrong. The physics has been validated over and over again. The reason is that the engineering is just genuinely, ferociously hard. And for decades, the funding wasn't commensurate with the difficulty of the problem. There's a famous graph that the fusion community has been showing since the 1970s. It plots projected timelines for achieving fusion energy against different levels of funding. The bottom line, labeled something like "Fusion Never," shows what happens with the lowest funding levels. And for much of the past 50 years, actual funding has tracked that bottom line. We've been underfunding fusion and then expressing surprise that it's taking a long time. But something has shifted. The combination of the climate crisis making the need for clean energy more urgent, the breakthrough in high-temperature superconducting magnets making compact machines feasible, the NIF ignition result proving the fundamental physics in the most dramatic way possible, and the influx of private capital from investors who see a market opportunity. All of these things together have created a moment that feels genuinely different from previous waves of fusion optimism. I want to be careful here, because the history of fusion is littered with moments that felt like turning points and turned out to be false dawns. Zeta in 1958, the tokamak excitement of the 1970s. Each time, the community thought they were close, and each time, new problems emerged that pushed the goal further away. But there are reasons to think this time might be different. The understanding of plasma physics is incomparably deeper than it was in the 1970s. The computational tools available, the ability to simulate plasma behavior in 3 dimensions, to model turbulence, to predict instabilities, these didn't exist a generation ago. The materials science has advanced. The magnet technology has advanced dramatically, with the Rebico high-temperature superconductors enabling magnetic fields that would have seemed like science fiction 20 years ago. And the engineering workforce has grown. There are more people working on fusion today than at any point in history. So, what does the path forward actually look like? Let's think about it concretely. If everything goes well, and that's a big if, but let's be optimistic for a moment. You could imagine a sequence of events over the next decade or two. Spark demonstrates net energy gain in a compact tokamak, proving that high-field, compact machines work. ITER, despite its delays, eventually operates with deuterium-tritium and demonstrates Q equals 10, validating the physics at scale. One or more of the private companies builds a pilot plant that generates electricity and feeds it into the grid, even if it's not yet economically competitive. And then the iteration begins. The same kind of iteration that brought the cost of solar panels down by 99% over 4 decades. The same kind of learning curve that made jet engines reliable enough to fly hundreds of millions of people every year. First-of-a-kind fusion plants will be expensive and finicky. Second-generation plants will be better. third-generation plants might be genuinely competitive with other forms of energy. And if that happens, if fusion becomes a practical energy source, the implications are almost hard to overstate. You'd have a source of energy that's essentially inexhaustible. The deuterium in seawater is enough to power civilization for billions of years. The energy density is millions of times greater than chemical fuels. There's no carbon dioxide, no air pollution, no risk of meltdown, no long-lived radioactive waste. The used components of a fusion reactor would be radioactive, yes, but the half-lives would be measured in decades, not millennia, and with the right choice of materials, the waste could be safely recycled within a century. Compare that to the spent fuel from a fission reactor, which remains hazardous for hundreds of thousands of years, and you start to see why people get excited about fusion. Think about what that would mean for a world struggling with climate change. Not just electricity, but industrial heat. The ability to produce steel, cement, ammonia without burning fossil fuels. The ability to desalinate seawater at scale, providing fresh water to regions that desperately need it. The ability to produce hydrogen or synthetic fuels for aviation and shipping. Fusion doesn't solve every problem. You still need transmission infrastructure. You still need to manage the grid. You still need all the other pieces of a modern energy system. But it addresses the hardest part, which is providing abundant, reliable, clean baseload energy. And I think there's something deeper here too, something that goes beyond the practical. The pursuit of fusion is, in a way, a statement about what humanity is capable of. We looked at the sun, this thing that's been burning in the sky since before there were eyes to see it, and we figured out what it was doing. We understood it. And then we set out to do it ourselves, not to destroy, but to build, to power cities and hospitals and schools, to give everyone on Earth access to clean, abundant energy. That's an extraordinary ambition, and the fact that it's taken longer than anyone expected, that it's been harder than anyone imagined, doesn't diminish the ambition. If anything, it makes it more impressive, because the people working on this, the physicists and engineers and technicians and students, they've kept going. Through funding cuts and skepticism and setbacks and the same tired joke about 30 years. They kept going because the prize is worth it. So as you lie there, maybe drifting off, maybe already half asleep, here's what I'd leave you with. Somewhere right now, at this very moment, someone is running a plasma experiment. Maybe it's at a national lab. Maybe it's at a startup in a converted warehouse. They're watching the data come in on their screens, watching the temperature climb, watching the confinement time stretch a little longer than last time. And they're thinking about all the problems that still need to be solved, all the engineering that still needs to be worked out, all the years of effort that still lie ahead. But they're also thinking about what it would mean if they get there, what it would mean for their children, for everyone's children, a world with clean, abundant energy. A world where the power of the stars is something we hold gently in our hands, not to destroy, but to light the way forward. And that thought, that quiet, stubborn hope, that's the heart of the fusion story. It always has been. Sleep well.